Welcome to this lecture on decoder design considering inverse narrow width effect. This is a part of module 2 combinational circuit design. So, today we will discuss the inverter design where we will minimize delay and then minimize the energy consumed per operation. So, in this we will use inverse narrow width effect as an aid. So, as we have discussed, the aim is to minimize delay of the decoder and maximize energy efficiency for that minimum delay. So, this is the decoder logic diagram, and here while when we optimize the circuit, we will find that we will keep inverters at the end, and in reality we may realize this as single inverter, and here we may have two inverters. I mean, the actual logic implementation could be a bit different, but in general this is the implementation, and we would add inverters at the end to reduce delay. So, as we had discussed in the previous lecture on buffers, when we add inverters, the number of stages increase, which increases the delay, and the load per stage reduces, which actually reduces the delay. So, there is an optimum number of stages which would actually minimize the delay. Okay, and for that minimum delay, we will then reduce the energy per operation. So, the procedure that we will follow is on the lines of the procedure that we followed for buffers in the previous lecture. So, we will start with an arbitrary but realistic value of width of the finger of N MOSFET for inverter and for NAND gate. We will keep it the same. The width of the finger of N MOSFET, we will keep it the same for both inverter and the NAND gate. We will then change the value of width of finger of the P MOSFET, so that pull up and pull down effective currents for the inverter match. So, that will match the output transition for pull up transition times for pull up and pull down. So, you will get a balanced inverter. Likewise, for NAND gate, for one of the input switching, okay, usually the lower input switching. Lower input switching, lower input in the series stack of N MOSFETs. So, for this case, we will adjust the value of WFP of the NAND gate, that is the finger width of the P MOSFET, such that effective pull up and pull down currents of the NAND gate match. So, for a single input switching, the pull up and pull down transition times of the NAND gate also now match. Now, keep the number of, for these values of, for the inverter this value of P MOSFET finger width, and for the NAND gate this value of P MOSFET NAND gate, and for the inverter and NAND gate both this value of N MOSFET finger width. We will keep number of fingers of each device to be 6. Why 6? So, for few number of fingers, the parasitic capacitance would change in a very discrete manner, but for large number of fingers, the parasitic capacitance would change almost continuously. So, therefore, our further assumptions that the parasitic delay remains constant, etc., these those would be valid for relatively large number of fingers. So, that is why we are taking a value which is not too large, but it is which would give us that continuous change in parasitic capacitance. That would be the case here. So, then with this number of fingers, we extract the values of logical effort and parasitic delay for the inverter and the NAND gate. Let us look at the logical effort and parasitic delay in terms of effective current. So, for the inverter, the delay for the inverter with WFN NMOS finger width and the corresponding WFP INWE being the PMOS finger width. For such an inverter, what is the delay? Delay is delta intrinsic delay into H electrical effort into parasitic delay into delta. So, what is this in terms of effective current? So, we have a scenario where we have this inverter, okay. So, this is the input capacitance C in. So, what is the value of delta here? Then delta comes out to be C in VDD by 2 times I effective. And what does the value of parasitic delay come out to be? Or parasitic delay of the inverter, it would come out to be Cp by C in. So, this would, the parasitic would come out to be this, okay, because we are defining delta. So, this is for the inverter. What about the NAND gate? So, here the delay of the NAND gate would be given by G NAND into delta into H plus P NAND into delta. So, what is this given by? Inverter C in into VDD by 2 times I effective the inverter, okay, delta, this is delta into CL by C in of the input B of NAND gate, that is H into G, which is C in of B by C in of inverter into I effective of inverter by I effective of NAND plus parasitic delay of the NAND gate. Where P NAND is again given by into delta is again given by C in inverter VDD by 2 I effective inverter Hmm. So, the parasitic delay of the NAND gate can be written this way. So, this is delta, the second factor is delta, and this one is the parasitic delay effectively. Here this and this are constant because they are for the template inverter with this size of PMOS finger and this size of NMOS finger. So, these two are constant, it is the ratio of these two is constant, and suppose you change the number of fingers in this template inverter, even then the ratio of C in inverter and C effective inverter, I effective inverter would be constant because they would both scale with number of fingers. So, this is also a constant because parasitic capacitance increases as the size of the gate and effective current also increases as the size of the gate. So, this is an overall a constant for a given finger width. So, this way we can calculate. So, what will we first do? We will extract the values of logical effort and parasitic delay of the inverter and the NAND gate from delay versus C out by C in plots, from the delay versus C out by C in plots. How would we do that? So, for the inverter we would have a delay versus CL by C in inverter versus delay of inverter. So, you have a straight line, the slope is delta and this is P inverter. Likewise, for the NAND gate you would have delay versus CL by C in B, that is input B, that is what we are seeing here in this case. That would again be a straight line with a certain slope. This slope is G NAND into delta and this is P NAND into delta. I am sorry, delta also multiplies here, right. So, this once we extract, but then when we change the finger width, we know how the threshold voltage varies with finger width, that we can know from a analytical function, or also we can do one simple thing. We can, as I have discussed in the previous lecture, we can just plot the threshold voltage versus finger width, which in our range of interest would be fairly a straight line, almost a straight line. So, using that relationship, linear relationship, we can get the value of finger width versus threshold voltage. So, once you know the threshold voltage from using the material covered in our previous lectures, you can estimate the change in effective current. You can estimate the change in effective current and that you can use. So, for this finger width, these finger widths, we extract the logical effort and parasitic delay, and for other values of finger width, we use these relationships, parasitic delay relationship, logical effort relationship and delta versus I effective relationship, and in parasitic delay of the inverter. So, all these relationships we use, and we for a change in finger widths, we know how the threshold voltage changes, how the effective current changes, and therefore, how the logical effort, intrinsic delay, delta, parasitic delays, etc., change. Okay. So, for each finger width, you need not extract out the values of logical effort and parasitic delay again and again. Now, as a step 4, you add inverters at the end. How will you add? As we did in the previous lecture for buffers. You will say that the delay for a given number of stages, for example, here in this path A1 to D0, you have 2 stages. For a given number of stages, n, you would have that the total delay of the path is logical effort of the path, here in this case G NAND into H NAND plus H inverter into delta plus P NAND plus P inverter into delta. You can write it this way. So, what is the optimum? We know that G NAND into G inverter, which is 1, okay, into H NAND into H inverter is a constant. What is it? It is G NAND into G inverter. So, G inverter is 1, it is G NAND into C out, the total output capacitance of the decoder, divided by C in 1. So, these are all given by specifications. So, this is a constant. So, if you want to deal with a constant, you would say that both the constant, the product is constant and the sum must be minimized. So, all the terms here, in this case 2 terms, both the terms should be equal, both these terms should be equal. If there are n number of terms, all the n number of terms should be equal in value, only then the product can be constant, as we had seen in the previous lecture. So, the delay for a given number of stages is optimized for all the logical efforts into C L by C in 1 to the power 1 by n. So, this should be logical effort of a stage, k stage, into electrical effort of the kth stage. So, then you would have minimum delay, and if you want to optimize the number of stages, so what would we do for that? We would again follow the reasoning that we used in the previous lecture. So, when we add number of stages here, the delays would increase because number of stages have added, number of inverter stages have been added to the output, as we are showing here. And when we but for each stage, you would again, this n would increase, and therefore, this is called stage effort. So, for each stage, the stage effort would reduce, n would increase as you add number of inverters. So, therefore, the delay per stage would reduce, but number of stages would increase. So, we need to find an optimum, as we did in the previous lecture. So, on the lines of previous lecture, if we go, we would find that the optimum number of stages would be given when you have an optimum stage effort for a kth stage, and this is again given by 0.71 P inverter plus 2.73. It fits on this line, as we had seen in the previous lecture. Therefore, optimum number of stages is given by natural logarithm of pi g into C out by C in 1 by natural logarithm of rho. This should be increased to the nearest integer. Till now, it is the conventional logical effort method, which is given by Sutherland, Sproul and Harris. Now, we modify the method considering that this is a near threshold circuit. So, with inverse narrow width effect, threshold voltage changes a lot, and therefore, the overdrive would change a lot. So, therefore, now we reduce the value of WFN. So, when we reduce the value of finger widths, threshold voltage reduces, so leakage current increases, delays reduce. All these three taken together, you need to find out that for minimum delay, what is the minimum energy that you can obtain. So, energy you do not know whether it increases or reduces, because energy is a product of leakage power and delay. So, you do not know whether it is increasing or decreasing. You do not. So, that one needs to find out. So, now when you reduce the value of WFN and WFP, that is finger widths of P MOSFET and N MOSFET in the template NAND gate and template inverter. So, you adjust WP, you reduce the value of WFN and adjust the value of WFP, so that you have balanced inverter and balanced NAND gate. And then, as we have discussed just now, we will estimate the values of delta, G NAND, P inverter and P NAND. Okay. So, once we have done that, we would then, for the changed values of these, we will again estimate the value of N optimum and rho, which is 0.71 P inverter plus 2.73. From this we obtain N optimum, which is natural logarithm of, which is product of all logical efforts, which is actually here only the logical effort of the NAND gate into C out by C in 1 divided by natural logarithm of rho. So, this we have done for the new values of intrinsic delay, logical effort, parasitic delays, which correspond to the new values of WFN and WFP. Okay. So, now we have got the new number of stages. With this number of stages, we know the sum of all C ins from k equal to 1 to k equal to n plus C out. So, this we call C effective of the entire circuit, and likewise we know the leakage current of the entire circuit, that is actually leakage power of the entire circuit. If you have n optimum number of stages, n optimum minus, so the leakage power would be given by sum of all the NAND gates into the leakage current of NAND gate plus the leakage current of sum of all the inverters, sum of leakage currents of all the inverters. This is sum of leakage currents of all the NAND gates. This is the leakage, average leakage current into VDD into the delay of the decoder. So, that gives me energy, leakage energy, and dynamic energy is given by C effective into VDD square. So, total energy is given by E dynamic energy plus leakage energy. So, now we do this exercise. So, we calculate the total energy as we have just discussed. Now, we check if this total energy is larger than the total energy which was obtained with the previous value of WFN. If that is so, then we will keep the previous value of WFN as the optimum value of WFN, because otherwise the energy increases by reducing the value of finger width. Otherwise, we will go for the new value of WFN and then we repeat from step 1. So, we keep on repeating until a total energy per operation is larger than the previous value that was obtained with the previous value of the WFN. So, in this lecture we have discussed a method to optimize minimize the delays of near threshold voltage decoder while minimizing energy also. So, we have used inverse narrow width effect in this method. Thank you.